In this video, we're going to be looking at Chapter 18D on graphing trigonometric functions. Remember from the last video that the sine curve and the cosine curve both looked pretty similar to something like this. Now, notice that this function would keep repeating itself over and over and over again if I was to go all the way to the right and all the way to the left. Also notice that the same pattern occurs over and over. Therefore, this type of function, both cosine and sine, are known as periodic functions because they periodically repeat themselves over and over again. Also notice that both of these functions have maximum values. Right? In the case of normal sine and normal cosine, these maximum values are 1. They also have minimum values. And the minimum values are -1 for both cosine and sine. Now the difference between these two maximums and minimums is twice the amplitude of these periodic functions. So if I was to take the distance from either the max down to the x-axis or the principal axis, or the height from the minimum to the principal axis, they would be the same. And I know they haven't drawn them the same or to scale here. But this value is called the amplitude. One other term that we need to look at is the period. And the period is the distance that the wave travels here, or this periodic function travels in one revolution. So if I was to pick any point on the function, and right now I'm picking the maximums, and if I look at the distance between any two maximums or any two identical points, that length is going to be the period of the function. And this is the unit of length that it takes for the function to repeat itself one time. So again, we have the maximum, we have the minimum, the amplitude, which is the height between either the max or the min and the principal axis. Oops, sorry about that, I misspelled principal. Principal. This is the principal axis. And we have the period. The distance between any two repeating points. Now let's take a look at the sine function again. Notice that the maximum value is 1. The minimum value is -1. And the principal axis is just the primary x-axis. So y equals 0. This is the principal axis. Y equals 0. And we have a max of 1 and a minimum of 1. So I can quickly find the amplitude. The amplitude, remember, is the distance between either the max or the min, and the principal axis. So in both cases, the amplitude is 1. Now let's take a look at the period. Remember, the period is how long it takes for the function to repeat itself. So if we start right here at the origin and we follow the curve around until we get back to the origin, or sorry, the x-axis, and notice I've already crossed the x-axis once here, but I'm on the way down, and at the beginning the curve is on the way up. So I want to make sure I come all the way back to that same point where the curve is coming back up. And notice the distance here is 0 to 2 pi. So the period of the sine function is 2 pi. Also notice that we're no longer using theta here. We've replaced the unknown angle, which we were using on the unit circle, with the value x. So this is an actual sine function. Also, imagine we know that we should know that the period is 2 pi because that's one full revolution of the unit circle. Imagine taking the unit circle here, and we could sort of roll it out. If we picked a point right here and we rolled the unit circle along the x-axis, it would sort of create this sine function here. Okay, let's quickly look at the cosine function as well. Notice for the cosine function, also have a max of 1 and a minimum of -1. So my amplitude, again, is 1. Also notice that the period is still going to be 2 pi, but at the origin I'm starting at the value of the function is 1. So if I follow the function until I get back to a y value of 1, I've gone 2 pi distance here. So my period, again, is 2 pi. So that's something to remember, that the period, amplitude, maximum, and minimum for both the sine and the cosine are all the same. The only difference is that the graph here of cosine has been shifted 90 degrees. We'll talk more about that in just a minute. Now we're quickly going to take a look at how we can change or alter the sine function and what happens when we put different numbers in different places within the sine function. So here's our first example. Okay, so on this graph, the red curve is y equals sine of x. This is our normal curve that we've been working with. And notice the maximum is 1, minimum is -1, amplitude is 1, and the period is 2 pi. I know it's 2 pi because 2 times pi, or 2 times 3.14, is just over 6. So if we multiply sine of x by 2, or we place a 2 in front of sine x, we get the blue curve. Notice what happens. Our maximum is now up here at 2, our minimum is down at -2, therefore our amplitude has been stretched to 2. The green curve, I've placed a -1/3 in front of sine x. That -1/3 does two things. It changes the amplitude so that my amplitude is now 1/3, but it also flips my graph across the x-axis. So this positive hump or hill has now become a trough, and this trough over here has now become a hill, all while changing the amplitude. Here's another set of graphs. Okay, again, the red curve is y equals sine of x, our normal curve. This time, I've placed a 2 right before the x. So in the blue curve, I have y equals sine of 2x. Notice what happens here. I still have a maximum of 1, a minimum of 1. So my amplitude is 1. But in one complete revolution of sine of x, I now have 2 complete revolutions on the blue curve. In other words, my period for the red curve is 2 pi, but my period for the blue curve is now pi. I'm going to repeat my graph sooner. Right, this point right here is pi. So the period for the blue curve is now pi. Look at the green curve. This is the graph of y equals sine of 1/2 x. And I don't quite have one full revolution, but you can see that this hill, this first hill, or the first half of a revolution, now goes the same distance as my normal period for sine of x. So I'm actually doubling the period in this curve. And the period for the green curve is now 4 pi, or double what it normally is. Let's take a look at a few more graphs. Okay, again, the red curve, normal, y equals sine of x. The blue curve is now y equals sine of x minus 2. And notice that the x minus 2 is in parentheses, and that's very important. And you'll see why when we look at the next set of graphs. So, in the blue curve, notice that this hump right here has been shifted to right here. Or in other words, this point, the origin on the normal y equals sine of x, has been shifted over to this point, 2 units to the right. And that's true for actually any point on the normal sine of x curve. If I take the first maximum and I go over 2 units, I'm going to hit the maximum, the first maximum on the blue curve. Likewise, in the green curve, where I have sine of x plus 2 being in parentheses, that first point has been shifted 2 units to the left. And the first maximum on the regular sine of x curve has been shifted 2 units to the left. Okay, one more set of curves to look at. Alright, last set, we have y equals sine of x in red again. And now for the blue we have y equals sine of x plus 2. Looks like the same function in the last curve, or the last set of graphs. However, there's no set of parentheses here. What happens is that I'm shifting this the x curve up. And actually, I'm sorry, I've written these in the wrong order. The blue curve is actually minus, and the red curve, or the green curve, is actually plus. So in this first curve, sine equals x minus 2, I'm actually shifting all the points down 2 units. Look at any point on the red curve, and it's just shifted down 2 units. Likewise, on the green curve, we have y equals sine of x plus 2. Any point on the red curve is shifted up 2. Any point, I go up 2. Otherwise, it's an identical curve to y equals sine of x. So let's talk about what all of these translations and transformations mean. I'm now going to write the function, or the sine function, in general terms that would encompass all of those translations and transformations. So we have y equals a times the sine of b times x minus c plus d. Now x is our normal angle value, and y is the value of the function after we've accounted for a, b, c, and d. So what are a? Well, a affects the amplitude. We saw that in the first set of graphs. A affects the amplitude. So if this is a positive number greater than 1, the amplitude is going to be stretched. If it's a negative number, the amplitude is going to be flipped. And if it's less than 1, or between negative 1 and 1, the amplitude is going to be squished. B affects the period. So if this number is a large positive integer, the period is going to be squished, and if it's between 0 and 1, the period is going to be stretched, and we saw that in the second set of graphs. C affects the horizontal translation. So if C is a positive number, the graph is going to be translated to the right because I'll have x minus that number. If C is a negative number, the graph is going to be translated to the left because I'd actually have x plus a number. And we saw that in the third set of graphs. And D is the vertical translation. And if D is positive, the whole graph is going to be shifted up. If D is negative, the whole graph is going to be shifted down. There's one more thing to consider about the variable b here. If I'm given b, I can find the period for that function by a simple calculation. Here the period simply becomes 2 pi divided by b. So in a normal sine function, y equals sine of x, b is just 1. It's that imaginary or invisible coefficient 1. So the period would be 2 pi divided by 1, or 2 pi. Well, that makes sense, because we know the period of sine of x is 2 pi. So the period for any sine function is simply 2 pi divided by b. Okay, let's take a look at a few example problems. The first example problem asks us to find the period of y equals sine of pi over 3. Well, remember from the previous slide that the period for any sine function is simply 2 pi divided by b. In this case, b comes from this term right here. B is really 1/3, because I can rewrite pi over 3 as 1/3 pi. I apologize here, this should not be a pi. I've been using pi. This should be an x. So let's get rid of these. This should be an x, this should be an x. So I'm talking about 1/3 x here, and the original function is y equals sine of x over 3. So again, here my b term is 1/3. In fact, this is the only term that I have that's new in this function. It's the only one I'm concerned about. So the period is really 2 pi divided by 1/3. But remember, dividing by a fraction is the same thing as multiplying by the reciprocal. So I have 2 pi times 3 over 1, which is 6 pi. And this is the period of my function y equals sine of x over 3. In this next example problem, we're asked to sketch the function y equals 2, cosine, I wrote cosine, this should be sine, 2 sine of x minus 1. And we're not allowed to use any technology. So first let's sketch a primary axis. And sometimes it's helpful to actually just sketch y equals sine of x. So I'm going to do that first. Y equals sine of x. Okay, we know that that function starts here at the origin, it goes up to -1, comes back down at x equals pi, goes down to -1, and comes back at 2 pi, or x equals 2 pi. This is 1, this is -1. And now we want to take a look at our sort of mutated function here. We have y equals 2 sine x minus 1. And there are a few things that we need to consider. The first thing that we need to consider is this 2 in front of the sine x. And sometimes it helps to graph these functions sort of in steps. So if we were just to look at 2 sine of x, that 2 we know would double the amplitude. So I'm going to sketch that here. It would double the amplitude, but it would not change the period of the function. All right, so that my new max would be 2, and my new minimum would be -2. Okay, so that's the first change to our function. The next thing that we need to consider, and the only other difference, is this -1 out here to the right. And remember that the -1, I'm not in parentheses here, that -1 shifts that green graph down one unit. So I need a little bit more room here. I'm going to move my graph up. And so that -1, I'm going to use blue now, shifts my entire graph down 1. So if this new max was 2, this max is now going to be 1. If this minimum over here was -2, the new minimum is going to be down here at -3. Okay, so I have 1 and -3. Otherwise, and actually every other point on that green curve gets shifted down 1. So this point right here gets shifted down 1. This point right here gets shifted down 1. All right, this point right here gets shifted down 1. And now I can sort of connect the dots. I can go up, down, hit the minimum, back up, and then I'm crossing the x-axis again. So notice that my primary axis has really been shifted down 1 as well. And this is my new curve, y equals 2 sine of x minus 1. And that's how you can really graph, without technology, most sine functions and cosine functions. Sometimes it's just easier to use a graphing calculator or your computer, and you can definitely do that to check your work.